Hello, today we're going to talk about 13.3, the arc length and curvature of a vector function. And so here I've got this curve drawn, and the curve is in blue and smooth. It's got a twist in it and everything. And the red line that's on here, you can see it's broken up and disconnected. What that is signifying is this idea that when we're trying to find the length of a curve, and we're trying to measure it, we have to measure it by these straight length um, measurements. And the idea is that you would take the distance between 2 points, you calculate that distance, and that's a good approximation of the length between those 2 points. But as you can see by the one that I've drawn here, the blue line is quite off, or the blue curve is quite off from the straight red line. So the idea is that we would make the distance between the points smaller and smaller and smaller and take a limit on that. And eventually we would come up with the exact length. And we would add all of those together. And there would be an infinite number of things that we would have to add together. And so what that means is that we are going to be taking an integral, because an integral is nothing more than a bunch of infinite sums. And so this representation down here is the infinite sums, or the infinite sum of the straight edges approximating the curve. And because we take the limit on the length of each of the straight edges, and then we take the limit on the sum, what we get is actually an exact answer, which is pretty cool. Now, that's just kind of giving you the background there. This formula that we have in here, this is going to be our arc length formula. It says that the length is going to be the integral between a and b, so that's talking about the beginning and the end of the curve, and those have to be t values. So if we're calculating arc length and we don't have t values, we have to somehow figure them out. The integrand itself is the square root of a sum of squares, which is coming from a Pythagorean theorem. And look at what the sum of squares is. It's a change in x with respect to t, and a change in y with respect to t. And so we could boil that, well, first we could look at that in 3D. We would also have to include a change in z with respect to t in our square root. And so this first one up here, this is coming from, so it comes from Pythagorean theorem, or distance formula. And then the one that is in the three-dimensional case, this is also coming from our three-dimensional distance formula. I find it's very nice to know where things come from because it might allow you to remember them better. Now, these formulas are given to you on your formula sheet. However, the way that they're given to you is in this more concise form that takes care of 3D and 2D. So if you remember what the magnitude of a vector is, it just means it's the square root of the sum of squares. So I have the magnitude of r prime of t, and r prime of t has components of x prime of t squared, and then y prime of t, that'll get squared, and then z prime of t, which will get squared, which is exactly what we're seeing up here on the second level. Okay, so this representation covers the 2D and 3D case. And so this is the formula that I give you on your formula sheet. You want to know it's there and you want to know how to use it. All right. So there's also a way to just get an arc length function rather than, oh, wait, before I go any further, really quick, because this is an integral of a magnitude of a vector, remember that the magnitude of a vector is a number. And so when you find arc length, you're going to get a scalar value. You better not be getting any vectors, okay? All right, so then the arc length function, this is just ever so slightly different. The idea with the arc length function is to come up with a function of t that would allow you to find the length of any portion of the curve from the beginning to some unknown value. And so the way we can define that is using this s of t, and the bounds of it are a to t, where the variable, the t up here is the variable stopping point. And then we change, instead of having r prime of t and dt in the integrand, we use what's called a dummy variable. And we use u typically for a dummy variable. And after we integrate and substitute everything in, we should end up with a function of t. And that function of t will allow us to calculate a length between any 2 points on the curve. We're not going to focus so much on that. We're going to focus more on, we've got a curve, we want to find out how long the curve is, okay? So in this example, we're going back to a problem that we saw in 13.1. It was a vector curve, and the function had components of cosine of t, sine of t, and t, and that was the slinky-looking helicoid. And we want to find the arc length of this curve between the points 1, 0, 0 and 1, 0, 2 pi. Remember that these are x, y, and z values that are being given to us in a point. Okay, and those are going to allow us to find a t value, our t bounds. So let's look at, we want to find the arc length. So the very first thing I would recommend is write down the formula first. L is going to be the integral from a to b of the magnitude of r prime of t dt. Always write down your formula first, because once you see that, you can find out, oh, I need to figure out a few things, and those are the things I need to plug in. So we're given r of t. With r of t, we need to find r prime of t. R prime of t, we just take a derivative of each of the components. The derivative of cosine is negative sine of t. The derivative of sine is cosine of t. And the derivative of t is 1. All right, then we need to find the magnitude of r prime of t. And so the magnitude is just, we're going to write that out. It's equal to the square root of the sum of squares. And if I square each of these terms, I get sine squared of t plus cosine squared of t plus 1. Remember your Pythagorean identity, sine squared plus cosine squared is equal to 1. And so this is going to be equal to the square root of 1 plus 1, or the square root of 2. Okay, so that gives us our integrand. What we need now are the a and b values. So we were given x, y, and z values. We need to know what r is going to give us for a t value. Remember that the components of r of t are x of t, y of t, and z of t. So I'm looking at that and I'm like, okay, so for 1, 0, 0, set that equal to, sorry about that, we had a power outage here at campus, so let me just start this sentence over again. We're trying to figure out our t value, and we've been given 2 x, y, z points. So what we do is we're going to take each of the points, I'll take 1, 0, 0 and write it as a vector and set it equal to my actual vector function, cosine of t, sine of t, and t. And the idea is to look at the components and say, well, if I have 2 vectors that are equal, then the components must be equal. So this means cosine of t is 1, sine of t is 0, and t is 0. Well, that third one kind of tells me that at the point 1, 0, 0, t is equal to 0. So that's my starting point. That's my A. And then I can do a similar thing for the second point for 1, 0, 2 pi. Oops, so make it into a vector and set it equal to the vector function, cosine of t, sine of t, and set each of the components equal to each other. Cosine of t is 1, sine of t is 0, and t is 2 pi. All right, that's what I'm after. The t is equal to 2 pi. That tells me b is equal to 2 pi. Now, just a really quick check, if t is 0, cosine of 0 is 1, sine of 0 is 0. So in that first point, that works. If t is 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0. So it works in all the components. All right, so let me go ahead and plug in these values to my integral. I have the integral from 0 to 2 pi. The magnitude of r prime was the square root of 2 dt. And that's a nice simple integrand. So when we integrate a constant, we get the constant times t. And we're going to evaluate from 0 to 2 pi. Substituting in, we get 2 square root of 2 pi minus 0. And so the exact arc length of this helicoid from 0 to 2 pi is 2 square root 2 times pi. And that's it. All right, let's look at the length of the curve. R of t is equal to 1 t squared and t cubed. And here they're telling us t goes from 0 to 1. So that's my a and my b value. Again, write out your formula. Arc length is the integral from a to b of the magnitude of r prime of t dt. So that means we need to find r prime, and then we need to find the magnitude. R prime is going to be 0, 2t, and 3t squared. The magnitude of r prime is going to be the square root of 0 plus 4t squared plus 9t to the fourth. It looks like each of the terms has a t squared in common, so I can factor that out and square root it. So it's t on the outside. That leaves behind 4 plus 9t squared. Okay, and that is my magnitude. Go ahead and plug everything in because I have it all. A is 0, B is 1, and the magnitude of r prime of t is t times the square root of 4 plus 9t squared dt. Now, the fact that I simplified my radical is extremely important. If I'm not willing to do that, then I'll never be able to integrate this. I need that t on the outside because I'm going to do a u substitute right now. So my u sub is, I'm going to let u be what's under the radical, 4 plus 9t squared. Then du will be 18t dt. But I don't have an 18 in my integrand, so I'm going to divide out an 18. So 1/18 du will be a replacement for t dt. Okay, now I typically do not change my bounds. I usually work out my u subs on the side and then I go back and I plug them in because I've been known to make mistakes when I change my bounds. So I'm going to look at this over here on the side. We're looking at just an indefinite integral, and I have a 1/18 to replace t dt. There's also a du, and then I have a square root of u du. Okay. Square root of u can be rewritten as u to the 1/2 power. And if we're integrating, remember we add to the exponent and then we divide by that sum. So if we add to the exponent, we add 1 to the exponent, 1 plus 1/2 is 3/2. And so then that means that we are going to, we're going to divide by 3/2, which is the same as multiplying by 2/3, and then u to the 3/2. And this simplifies just a little bit more to be 1/27 u to the 3/2. All right, so that is my antiderivative. I'll go back to my original problem. It's 1/27. And instead of writing u, I'm going to write 4 plus 9t squared, all to the 3/2 power. And then we're going to evaluate this from 0 to 1. When I plug in 1, I'm going to leave my 1/27th out on the outside. When I plug in 1, I get 4 plus 9, which is 13 to the 3/2 power, minus when I plug in 0, I'm left with 4 to the 3/2 power. And about the only simplification I can do here is to rewrite this as 1 over 27 times 13 square root of 13 minus 4 to the 3/2 power. The half part tells me take the square root, so square root of 4 is 2, and then 2 cubed is 8. And that would be my final answer, 1/27 times, in quantity, 13 root 3 minus 8. All right. Next topic in this section is curvature. And when we're measuring curvature, we're just trying to figure out how fast a curve is changing direction and at a particular point. And another way to think of that is like, how curvy is this curve, okay? And as long as our vector function doesn't have any holes in it and it's smooth and has no sharp edges or anything, then we can calculate this value. We have a couple of different ways to calculate it, and I give these on your formula sheet. So just be aware of that, and then also be aware of how to use them and which one might benefit you more. All right. So now that we have this formula, we'll try to use it. So the K of T, it's not actually K, it's kappa. That's a kappa. So kappa of T is going to equal the magnitude of T prime over the magnitude of R prime. That's one way to calculate it. Another way is the magnitude of the cross product of R prime and R double prime over the magnitude of R prime all cubed. So we have a couple of different ways that we could look at this, and we'll try one of each. All right, in this next example, we're going to tie a few things together. The first one, we're using a curve that we've been using, this helicoid. R of t is equal to cosine t, sine t, and t. And then this first question, we're being asked to find the unit tangent vector at a particular point. And this is an x, y, z value. And if I was to be able to find a unit tangent vector, I have to first remember what a unit tangent vector is. It's t of t is equal to r prime of t over the magnitude of r prime of t. So it's a tangent vector just made into a unit vector. That's it. Now, if I want to find the unit tangent vector at a point, I need to know the t value. So I need to take this point, 1, 0, 2 pi, set it equal to the vector function cosine of t, sine of t, and t, and set the components equal to each other. Now we've already done this one, and we did it on the previous page for arc length. And for this one, it's t is equal to 2 pi. So we're being asked to find the unit tangent vector at the point t equals 2 pi. All right, so I need r prime. R prime of t is equal to minus sine of t cosine of t and 1. I need the magnitude of r prime of t. We have calculated all of these before in the previous problem, but it's fine to redo it. We square each of the components of r prime. We get sine squared of t plus cosine squared of t plus 1, which is going to be the square root of 2. So t, the unit tangent vector as a function, is equal to the r prime of t, which we found to be negative sine of t, cosine of t, and 1, divided by the magnitude of r prime of t, which is the square root of 2. So this is the unit vector, unit tangent vector, as a function. But we want to find it at t equals 2 pi. So that means we're going to evaluate our unit tangent vector at 2 pi, which means everywhere we see a t, put in 2 pi. So we have the 1 over square root 2 times the vector negative sine of 2 pi, cosine of 2 pi, and 1. Sine of 2 pi is 0, so I have 1 over square root 2, 0. Cosine of 2 pi is 1, and then the last term is 1. And that is our unit tangent vector at the point 1, 0, 2 pi. Now we're being asked to find the curvature at that same point. And so I go back up to my curvature, and it looks like I want to use this first form because it says you need the magnitude of t prime and the magnitude of r prime. I've already calculated t, and t isn't too bad, so finding t prime won't be too bad. I'd much rather do that than find r double prime and then calculate a cross product. So, you know, it's good to decide which one's going to be easier for you. All right, so I'm going to use kappa of t is the magnitude of t prime over the magnitude of r prime. Okay, now I found t of t as a function up above. That means that's what I need to find the derivative of, t prime of t. The constant in front is 1 over square root 2. That won't change. But inside, the derivative of negative sine is going to be negative cosine of t. The derivative of cosine is negative sine. And the derivative of 1 is 0. And then I need the magnitude of t prime. And so that's going to be the square root of cosine of t over square root 2 squared, I guess that's a negative, plus the negative sine of t over the square root of 2 all squared. And then that's going to add up to be the square root of cosine squared of t plus sine squared of t over 2, which finally leaves me with a 1/2 under a square root, or 1 over the square root of 2. Okay, now up above, I already have the magnitude of, whoops, I didn't mean to cross that out. I already have the magnitude of r prime of t right here. So I'm going to use that in my kappa of t, and I'm going to use my magnitude of t prime of t to get, we got, all right, square root of 2, 1 over the square root of 2 on top. And in the bottom, I have the square root of 2, and that's going to simplify to just be 1/2. So what's interesting about this one is that I never even had to plug in t equals 2 pi because both of my magnitudes simplified to be scalars. That's the only reason, though. That will not always happen. All right. Next thing to talk about, the principal unit normal vector. We're also going to be looking at a binormal vector, but we're not going to stress about it because it's really not an objective of this course. So let's see. The principal unit normal vector is, let's see, it's always normal to the unit tangent vector. So I've got these pictures here. And I think, let's see, which one is a really good one to look at? I think maybe this one over here kind of shows it well. We see our t vector here, the tangent vector, it's a unit, and it runs tangent to our curve. The unit normal vector is kind of pointing inward on the curve. Notice this is a concave down curve, and the unit normal points into that concavity, kind of points outward or inward. And then the binormal is actually a cross product of the unit tangent and the unit normal, so it points perpendicular to both of them, and that is their relationship. The three of them are perpendicular to each other. And so I've got a few different images to try to make that clear. I think actually these pictures here make it even more clear because you can see that that right angle right there drawn with a square or a box. Okay, let's look at how we're going to calculate these. We already know the unit tangent vector. Now the unit normal vector is going to require more derivatives. So you'll have to find your unit tangent vector, and then you find its derivative and you find its magnitude, and you find the ratio of those, and that will be the unit normal vector. The binormal vector, as I said, it is normal to both the unit tangent and the unit normal vector, so we would just find the cross product of those to come up with the binormal. But this we will not be using. But it might show up in other classes. Okay. Now we put them all together and they form what's called the TNB frame. And this is typically seen in, like if you're studying mathematics, we would see it more in differential geometry. And if you're studying more your physics and engineering, you're going to see this applied to the motion of spacecraft. Okay. But like I said before, we're not really going to be looking at the binormal. It's just like a serious exercise in lots and lots of calculations. We're going to focus more on just the unit tangent vector and the unit normal vector. So I'm back to the same curve in this example, the helicoid. R of t is cosine sine of t. We're supposed to find the unit normal vector at the point 1, 0, 2 pi. Now remember, this is the same point as before, right? So we look at t is equal to 2 pi, so that's our t value. If we want the unit normal vector, we need to know what it is. The unit normal vector will be t prime of t, and then we're going to divide out the magnitude of t prime of t. Now I want to recall, for the sake of time, that we found t prime of t, right? Let's go back up here. T prime of t, here it is. I'm just going to duplicate that and drag it down. Okay. Oops. Got to keep dragging it. So our t prime of t we have here. And so we don't need to calculate that again. But we do need to find the magnitude of that. I believe we calculated that as well, but let's go ahead and do that again. So we have t prime of t in magnitude will be the square root of negative cosine of t all over the square root of 2 squared plus negative sine of t over the square root of 2 all squared. And then when we simplify that, this becomes cosine squared of t plus sine squared of t over 2, which reduces to the square root of 1/2, or 1 over the square root of 2. Okay, so n of t, the unit normal vector, is just going to equal 1 over the square root of 2 times negative cosine of t, negative sine of t, 0. Let me move these guys over a bit. Over the magnitude of t prime of t, which is 1 over the square root of 2. So those 1 over square roots of 2, those go away. And our unit normal vector as a function is going to be negative cosine of t, negative sine of t, 0. Unit normal as a function. But that's not what we were asked for. We were asked to find it at t equals 2 pi. Then we're looking at the unit normal evaluated at 2 pi. So we plug that in, we get negative cosine of 2 pi, negative sine of 2 pi, and 0. And this simplifies to be negative 1, 0, 0. And that is our unit normal vector. Okay. So not too bad, not too bad at all. Now I have a few extra examples, and this is in case anybody's really struggling with these curvature functions. and some of the calculations, and pretty much all of the calculations are included in the unit tangent and then the unit normal as well. So it's a whole lot of finding r primes and r double primes and t's and t primes and whatnot. So in this particular example, again, I'm going to write out my formula that I need. The curvature of t is, now here I'm starting from scratch. I have r of t. I do not have r prime. I don't have t. I don't have any of those things. So in this particular case, it would probably be easiest for me to find r prime cross r double prime all over the magnitude of r prime cubed. That's our formula. And again, it's on the formula sheet. So I need to find r prime first. R prime is going to be 1, 2t, and 3t squared. R double prime is going to be 0, 2, and 6t. And then the magnitude of r prime, well, actually, first I'll find my cross product. The cross product of r prime and r double prime will be, I got my little cross product here, so we'll get a 12t squared minus 6t squared. And then I have 1 times 6t, so 6t minus 0. And then I have 2 minus 0. This simplifies to be 6t squared minus 6t and 2. Okay. Now I need the magnitude of this. So the magnitude of r prime cross r double prime is going to be the square root of 36t to the fourth plus 36t squared plus 4. Okay. And then what else do I need? I need the magnitude of r prime as well. And so I'll go back up to my r prime. I'm going to get, the components are 1. So I'll get a 1 squared, which is 1. My other component is 2t. Square that, we get plus 4t squared. My third component is 3t squared. Square that, we get 9t to the fourth. Okay. Now, I don't want my curvature as a function. I want it at the point 0, 0, 0. If you compare 0, 0, 0 with the curve function itself, t squared, and t cubed, we're left with concluding that t must be 0. Okay? So I'm trying to find at t equals 0, kappa of 0 is the magnitude of r prime of 0 crossed with the magnitude of r double prime of 0. Sorry, the magnitude of the cross product of r prime of 0 and r double prime of 0, all divided by the magnitude of r prime of 0, all cubed. So I'm going to plug in all these zeros. We found our cross product and its magnitude. We need it evaluated at 0. So plug that in here. We get 36 times 0 to the fourth plus 36 times 0 squared plus 4. In the bottom, I have first my parentheses because I am going to have to square everything or cube everything on the outside. Inside I have 1 plus 4 times 0 squared plus 9 times 0 to the fourth. And I simplify all of this, and on top I get the square root of 4, and in the bottom I have the square root of 1 cubed. And this simplifies very, very nicely to just be 2. Okay. So I have a curvature of 2 for this twisted cubic. All right, last one. Find the curvature of this really kind of horrible vector function. This one's kind of intense because it's got a lot of function going on in each of the components. So we have a curvature, or sorry, we have a function r of t. Components are e to the t cosine and e to the t sine and t. And we want to find the curvature at the point 0, 0, 0. So let's see what we got to do. We need to find our derivatives, r prime and r double prime. I'm going to go with kappa of 0 Oh, actually, yeah, we need to conclude that t equals 0 first. Hold on. So note that if 0, 0, if we were to set this vector function equal to 0, 0, 0, we're forced right here and here to conclude that t is equal to 0. Okay, so we're going to find the curvature at 0 is equal to the magnitude of r prime of 0 crossed with r double prime of 0 over the magnitude of r prime of 0 all cubed. Now, I can't evaluate my function and then find my derivative. I have to find all my derivatives first. So let's work on that. R prime of t is equal to, all right, I have a product rule in each of these. So I'm going to get e to the t cosine of t minus e to the t sine of t in the first component. Second component gives me e to the t sine of t plus e to the t cosine of t. Third component leaves me with a 1. Okay. Next is r double prime. Actually, let me rewrite my r prime so that I'm not doing 4 product rules. Factor out an e to the t and leave behind a cosine of t minus sine of t in both of the first 2 components. So e to the t and then sine of t plus cosine of t and then 1. Okay, r double prime of t is e to the t times cosine of t minus sine of t plus e to the t times minus sine of t minus cosine of t. I have to write my vector on a few lines. My second component is e to the t sine of t plus cosine of t plus e to the t times cosine of t minus sine of t. And then the derivative of 1 is 0. Okay, before I go any further, I'm evaluating both of these at 0 because this is a mess. You definitely don't want to try to find magnitudes or cross products with these. So r prime of 0 is equal to e to the 0 times 1 minus 0. E to the 0 times 0 plus 1 and 1, which simplifies to just be 1, 1, 1. R double prime of 0 is equal to e to the 0 times 1 minus 0 plus e to the 0 times 0 minus 1. That's the first component. Second component, e to the 0 times 0 plus 1 plus e to the 0 times 1 minus 0 and then 0. And this simplifies to be 1 minus 1, so it's 0 in the first component, 1 plus 1, so that's 2 in the second component, and it looks like 0 in the third component. Okay, those are a lot easier to find cross products with than magnitudes. So that's my next step. R prime of 0 cross R double prime of 0. We have our I, J, K, 1, 1, 1, 0, 2, 0. This is going to give us 0 minus 2, negative 0 minus 0, and then 2 minus 0, which gives us a negative 2, 0, positive 2. Okay, now we need a magnitude of that. The magnitude of r prime of 0 crossed with r double prime of 0 is the square root of 4 plus 0 plus 4, which is 2 root 2. Okay, what else do we need? That was just the numerator. All right, we have our numerator. Okay, now we need our prime of 0 in magnitude and then cubed. Okay, so the magnitude of our prime of 0 is going to be the square root of 1 plus 1 plus 1. These are all squares, so it's just the square root of 3. and then we need that cubed. So this is going to be square root 3 all cubed, or in other words, this will be 3 square root 3. Okay, we have what we need. Our curvature at 0 is going to be this magnitude of r prime of 0 crossed with r double prime of 0 over the magnitude of r prime of 0 all cubed, which gives us 2 square root 2 over 3 square root 3, and we are done. Okay, so this last example was really to stress to you how even though this was a lengthy problem, I did make things easier on myself by very quickly evaluating my derivatives and not trying to find magnitudes or cross products with them. That would just be insane. So keep that in mind as you do your homework. And if you have any questions at all, please reach out.